Now we will discuss how the numbers are going to be represented in sign magnitude representation and 2's complement representation. If you just see here, the number of bits required for representing the numbers, they are going to follow 4-bit method. So in 4-bit representation, okay, so we have four separate positions, okay, out of which one bit is always reserved for the sign bit. Okay, this is for the sign bit. So if it is 0, it is indicating for positive numbers, and if it is 1, it indicates negative number. Okay, so one bit is always reserved for sign out of the total bits. So the remaining 3 bits are available for us to represent the magnitude. So one bit for sign and the remaining bits for available for magnitude. So with 3 bits, how many symbols you can generate? So 2 power 3, totally we can generate 8 symbols. Okay, so it always starts with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then triple 1. So totally 8 symbols. So starting from the decimal number 7 to decimal number 0 to 7. Totally 8 symbols is possible for us to represent in 4-bit representation. Okay. Now if you take plus 8, the binary equivalent of plus 8 itself is extending to 4 bits. So I cannot represent that with 4-bit representation because I need one more bit. Okay, this one more bit is reserved for sign bit. So if it is plus 8, I have to use 0 here. If it is a minus 8, okay, we have two representation. One is sign magnitude representation. In sign magnitude representation, what we told, the 0 will be changed as 1 because it is a negative number, and whatever is the magnitude will be the same. Okay, and if it is going to be 2's complement representation, here what we will be doing, you will be writing the positive equivalent of the given number, and you will take 2's complement of the positive number. So original number is 0, 1, 0, 0, 0. You have to take 2's complement of this number. So for minus 8 in 2's complement representation, how it will look like? So this 0 will be copied as such, this 0 will be copied as such, this 0 will also be copied as such, this one also will be copied as such. I told the shortcut, you keep copying all the bits till you encounter the first one. Okay, till you encounter the first one, you have to copy as such. Then the remaining bits, you have to flip it. Of course, the remaining bit is 0, so you have to flip it, change it to 1. Okay, so this is going to be the 2's complement representation of minus 8, and this is going to be the 2 sign magnitude representation of minus 8. Of course, for all these patterns, we just see there are 5 bits required. So with 4 bit, we will not be able to store plus 8. So only they have given it as a dash. Okay. And another important point to be remembered is for all the positive numbers, if you just see the pattern, it is going to be the one and the same for sign magnitude and also 2's complement. So both for positive numbers, there is no variation in all the 3 representation, whether it is going to be sign magnitude or 1's complement or 2's complement. For all the positive numbers, it is represented in the same manner. Only for negative numbers, there is a difference. Now we will just see how plus 0 is going to be handled. Plus means we will be putting 0 here, and the magnitude is 0, so all the bits are 0. In sign magnitude representation, we will have like this. For minus 0, for minus you will be putting a 1, and then for all the remaining magnitude it will be 0. So this is plus 0 and this is minus 0. Whereas if you just take 2's complement representation, for plus 0, it is going to be 0. This is for sign 0 plus, and then triple 0. For negative 0, what we have to do? We have to take 2's complement. For 2's complement, what is the rule we have told? So you copy all the bit patterns till you encounter the first one. So you have not encountered first one. So this is also same. So as far as 2's complement method is concerned, plus 0 and minus 0 is going to be having the same pattern. So we are not going to repeat the pattern. You are going to use only 1 plus 0. There is no concept of minus 0 when we go for 2's complement representation. This is the main important reason why we follow 2's complement representation in computers. And there could be a question that why not 1's complement representation? 1's complement we have, see how we will represent plus 0 and minus 0 in 1's complement. So plus 0 it is going to be 0, 0, 0, 0, and for minus 0 in 1's complement representation you have to take 1's complement, so it will be 1, 1, 1, 1. So we will be having two different patterns for plus 0 and minus 0, and if you follow these two patterns there will be a confusion whether it is going to represent minus 0 or plus 0. So in order to avoid this ambiguity, we are just going to follow only 2's complement where we don't have any separate pattern for minus 0. Now we will just see how the negative numbers are going to be represented. For negative numbers, what is the rule? If it is plus 6, okay, you first write the magnitude. The magnitude is 110, and then one bit is reserved for sign bit. This is plus, so you'll be having it as plus 0. And for minus 6, in 2's complement representation, how you will write? Okay, so you will take 2's complement. For that, you have to copy 0. This 0 will be copied as such. This 1 also will be copied as such. So you scan the pattern from the right. You copy all the bits till you encounter first one. And all the remaining bits have to be flipped. So this 1 should be changed to 0 and this 0 should be changed to 1. So this is going to be the 2's complement representation of minus 6. Okay. So like this, we can just write all the 2's complement values. Of course, we are not worried about the biased representation. You just the computer system is going to follow 2's complement, and we the manual operation will be referring to the sign magnitude representation. So it is enough that if you are clear with both this normal sign magnitude representation and 2's complement representation. We will now discuss how the sign bit extension is going to be handled in these representation. Okay, now let us take a number, the same number, maybe we can take plus 6. Plus 6, okay. So the plus 6 number, it can be represented in sign magnitude and also in 2's complement form, okay. And to start with, we will just see how it is going to be used, how it is going to be generated using 4-bit pattern. So for plus 6, the plus is indicated by 0, and for 6 it is going to be 1, 1, 1, 0. So this is going to be the binary equivalent of plus 6 with 4-bit representation in sign magnitude. In 2's complement also we will be having the same method. So as I told already, for positive numbers there is no change in the patterns. Okay. Now coming to the negative numbers, only negative numbers are going to be handled differently in both these methods. For sign magnitude representation, what we told, this sign bit alone will be changed to 1. Okay. And the remaining bits will be magnitude will be represented same way. So it is going to be 1, 1, 0. So this is going to be the pattern followed for minus 6 in sign magnitude representation. Now coming to 2's complement representation. For minus 6, how you will represent? So this is going to be 0, and this one also will be copied as such, and this one will be flipped to 0, 0 will be flipped to 1. So this is going to be the 2's complement representation of minus 6. So for plus 6 and minus 6, we have discussed how sign magnitude is going to be followed, how 2's complement is going to be followed using 4 bits. Okay. Now I want to extend the number of bits used for storing the numbers. So instead of 4-bit, I am just going to change it to 8-bit. Okay, how it is going to be followed, that we will see now. For plus 6 and minus 6, we have 8 positions, 3, 4, 5, 6, 7, 8. Okay, this is for sign magnitude, and again we will have the same pattern for 2's complement, also 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So for sign magnitude representation, you will just copy the number like this 0, 1, 1, 0. Okay. Because it is positive, the first bit will be 0, and all the remaining bits, okay, this unused extended bits, it will be always filled up with 0. So this is going to be the method followed in sign magnitude. So the first one is going to be the sign magnitude. The second column is going to represent for 2's complement. Okay. Now, for minus 0, how you will write? So, this 0 will be copied as such 1, 1, 0. So, already we have discussed, sorry, I think we have to change the negative number, change it for negative number. So, for minus 6 in sign magnitude representation, what is the original number? It is going to be 0, 1, 1. Okay. Now, you please listen. This is the sign bit. So, we already told MSB will be the sign bit. So, we have to copy the sign bit in this MSB position, and all the remaining bits, okay, whatever is 1, 2, 3, 4, 5, 6, 7, one more bit. So, all the unused bits will be all filled up with zeros. So, this is how you are going to extend the bit position. So, if it is 4-bit, you will be representing like this. If it is 8-bit, the leftover bits will be filled up with zeros, and you should ensure that the sign is going to be noted down only in the MSB. All the remaining unused bits will be filled up with zeros. So this is going to be the system followed for sign bit extension with respect to sign magnitude. Now coming to 2's complement representation, how we are going to do the sign bit extension. For plus 6, what is the original number? It is going to be 0, 1, 1, and for plus it is 0 here. So having written like this, now in 2's complement representation, what we have to do, we have to copy the sign bit. This is the earlier sign bit, and now we have to copy all the remaining unused bits with the sign bits. So you'll be copying 0, 0, 0, 0. So as far as positive numbers are concerned, I already told there is no difference between sign magnitude and 2's complement. Now how it changes for negative number, that alone you have to observe here. So for minus 6, okay, how we are going to do in 2's complement representation for minus 6, already we had this number. So you fill up this number 0, 1, 0 and 1. So this is going to be the earlier sign bit. Now I am going to extend to 8 bits, okay. If I am going to extend to 8 bits, what I should do, I should copy the sign bit to all the remaining bits. So all the remaining bits should be copied with the sign bit. So I have to copy this 1, 1, 1, 1. Now if you observe, what is the difference here? Here the sign bit alone is set to 1 and all the unused bits are initialized with zeros, whereas here the sign bit is 1 and the sign bit is only extended to all the remaining bits. Whether it is going to be 0 or 1, uniformly you can follow this method. So all the extended bits will be copied with the sign bit. So this is the system to be followed for 2's complement representation. Now we have just discussed how the numbers are going to be represented in sign magnitude representation, 2's complement representation, and we have also learned how to extend the sign bit. Okay,